In this video, I will discuss longitudinal waves, specifically sound waves, and their unique properties. Now, in another video, I did talk about longitudinal waves briefly. So once again, what is a longitudinal wave? And it says, waves in which the movement of the medium, for example air, is parallel to the wave's direction of travel. And here's a representation of a longitudinal wave. And in this representation, here's what I want you to realize. What we have are air particles. And in certain regions, like here, the air particles are close together, so the pressure is higher. But in other areas, the air particles are further apart, so the air pressure is lower. Now, what you have to imagine is this compressed wave is moving in one direction. Since this type of wave is difficult to visualize, unlike a transversal wave, which looks like a sine wave, here is a video that gives you a good example of how a longitudinal wave moves. Note, the compressed region represents higher air pressure. And I want to stress a few facts about longitudinal waves. First of all, remember that the air molecule really is not traveling from one point all the way to the other end. The air molecule stays in a certain region. It's only the waveform, the compression, that's actually moving. Another thing to note is, for the midterm exam closed book, know the difference between a transverse wave and a longitudinal wave, specifically how they move. In a transversal wave, the wave moves horizontally, but the particles move up and down and stay in their location. In a longitudinal wave, the wave moves horizontally and the particles oscillate horizontally in a specific location, but they never travel with the wave. And here's something else I'd like to point out about sound waves, and that is the speed of sound is temperature dependent. As the air temperature increases, the speed of sound increases. This is information that you might need to know for the closed book part of the midterm exam. So quickly, I just want to give you a good example of how air temperature can affect the speed of sound and what effect that will have on what you hear. Now, the example that you see on the left, this is trying to show you that if the air close to the surface of the earth is cool as compared to air above it, then air that's running straight across horizontally will pretty much go right to the receiver. However, for the waves that start to go up into upper atmosphere, they will start to bend towards the blue region again. Now, this is a very unique effect that I've experienced. So imagine that the source is a train, and that between the train and the receiver, you have houses, buildings, and all that stuff. So normally I would not hear the train whistle. But when it's wintertime, because the ground gets a lot colder than the upper atmosphere, I can suddenly start to hear the trains, because the sound from the train bends and comes over to me, the receiver. Now, let's look at our example in B. Here, this would be like the summertime. The ground's really hot, but the air above it is cooler. If you're trying to talk to someone, the receiver, the sound waves will pretty much go straight to that person. However, if the receiver is far enough away, that sound wave will actually start to curve upwards into the upper air. And that means you could be yelling at them, but they will not be able to hear you because the sound wave has bent or refracted into the upper air. I want to quickly talk about another special property of sound waves. And that is, sound waves can undergo diffraction. That's just a fancy way of saying that sound waves can bend around objects. And as a good example of this, look at this picture here. If you've got a radio playing here, the person on the other side can hear that music even though they cannot see the radio. And that's because when the sound waves go out, as you see on the right image, they spread out and they can actually go around corners and through openings. By the way, also water waves exhibit the same behavior. Now let's talk about another special property of sound waves, and that is their speed through different materials. Here's a chart. And here's what you'll notice. When we're talking about gases, such as air, notice that at 20 degrees Celsius, the speed of sound is 344, but at 0 degrees Celsius, it's 332. So here, this is showing us that As temperature increases, the speed of sound increases. But notice that in hydrogen, a different type of gas, the speed is actually higher. Also notice that in water, the speed of sound is higher than it is in air. Now let's take a look at some of our metals, iron and aluminum. Notice how much faster the speed of sound is compared to the speed in air. Now, what do we mean the speed of sound in iron? Well, I'll give you a good example of this. In the old days, when someone wanted to know if a train was coming, they would not listen for the sound of the whistle. What they would do is they would put their ear on the track, and that way, if a train was coming, they would be able to hear the train, because sound waves traveling in metal will travel farther and faster than sound waves in air. Now I'd like to discuss sound intensity. While a string transmits energy along a line in one direction, sound waves transmit energy over a volume of space. For sound waves, we are more interested in the concentration of power as power over area rather than the total power. So what we have here is a sphere, and at the center of the sphere, there is some type of sound source. And what we're showing here is as the sound wave moves out, the area it's got to cover becomes larger and larger. What that really means is the intensity of the sound, or in other words, its loudness, decreases. By the way, this is very similar to a light bulb. As you move away from a light bulb, the intensity of the light also decreases in the same way, or in other words, its brightness decreases. Now, I need to warn you, what we're talking about here is a source in which the waves can go out in all directions. We're not talking about something where there's a reflector, for example, a flashlight. In that case, this rule would be violated. So here's our definition of sound intensity. It's just simply the power over the area, but perpendicular to the area. For example, imagine a sound wave moving out from the center of a sphere. As it travels, it will eventually hit the sphere's surface, but it will hit the area of the sphere perpendicularly. That will be the sound intensity. It will be given in watts per meter squared. So something that's going to be related to sound intensity, and we'll be using an I to represent sound intensity, is the sound intensity level, which we symbolize with the letter beta. So be very careful because they sound the same. One is sound intensity, the other one is sound intensity level. So here's the deal with sound intensity. It is not a linear function, it is a logarithmic function. What do I mean by that? Well, think of sound intensity as corresponding to the sound's loudness. If I were to double the sound intensity, the loudness does not double. And that is because sound intensity has a logarithmic behavior. So what we do is we come up with a new way of describing loudness with the sound intensity level, and this formula is able to take care of the logarithmic behavior of sound intensity. So here what we have is beta is the sound intensity level in decibels. We abbreviate that as dB, and I is the sound intensity, which is once again watts per meter squared. And note the following. The layman's term for sound intensity level is loudness. The range of human hearing is usually between 20 Hz to 20,000 Hz. Whenever we wish to determine the sound intensity level, we need to use a reference sound intensity, and that is the value I sub O equals 1 times 10 to the negative 12 watts per meter squared. So that is a standard intensity level, and this happens to correspond to 4,000 Hz. At this sound intensity, the sound intensity level, that is beta, would be 0 decibels. A sound intensity of 10 to the 12th times the reference sound intensity is considered to be very painful. Therefore, sound intensity level for acoustic pain is 120 decibels. Because sound intensity I varies over 12 magnitudes of order, the sound intensity level, beta, is expressed on a logarithmic scale. Now I'd like to show you the formula chart that you may need to use on the homework assignment or on the midterm exam. And once again, what I've done here is I put down the units with this symbol. So when we talk about sound intensity for point A, it's going to be watts per square meter. When we're talking about the location of point A, it will be in meters. Now, I want to warn you about a common mistake students make when using these formulas, and that is forgetting to square R. So if you discover that you did this, then I recommend that you highlight the 2 in the formula. This way, whenever you use the formula chart, you'll see that highlighted 2. Another thing that I know is some students have difficulty using the square root symbol on their calculator, so I would tell you to do this portion here first, get a number, and then take the square root of that number. And you'll notice that the formulas for IB and RB are basically the same thing. The only difference between A and B is A is considered to be the first location, and B is considered to be the second location. Now here's a continuation of the formula chart. This time we're going to be talking about sound intensity level, which is represented by the beta and is given in units of decibels, dB. Be careful when dealing with sound waves, make sure you pay attention to the terms sound intensity level, which is beta, and sound intensity, which is I. Once again, the sound intensity is given in watts per meter squared. Now let me return to the sound intensity level formula. The key thing I want to point out here is you will be using the log key on your calculator, not the ln key, which is the natural log key. Notice in this formula, you'll take your sound intensity and divide by the reference sound intensity, which I have given here. Now let's turn our attention to the sound intensity formula. Notice here what we're doing is we're taking 10 to the power of beta divided by 10. On most calculators, you can carry out this calculation in the following manner. Enter the value for I sub naught. Hit your times key, enter 10, hit the caret key, which is the power key on your calculator, hit the parentheses key, enter the beta value, hit the divide key, enter 10, close parentheses. Hit equal or enter, and that will be your answer.